Today we're going to talk about a mass that's oscillating on a spring that is hanging. Now, when we have a situation like this, where a mass is hanging from a spring, we have a complicated thing going on. We know that simple harmonic motion happens when we have a restorative force, a force that's restoring the object back to its equilibrium position when it is displaced. And that restorative force has to be directly proportional to the displacement. So this here, y equals 0, is this spring's equilibrium length if there's no mass on it. A mass was put on it, and now it goes down to z equals 0, which is the equilibrium position for the oscillation. The object oscillates between B and E, maybe. Those look equally equal distances from z equals 0. So this spring can only pull, it can't push. And so the restorative force for this object, when it's down here, the restorative force is the spring force upward, minus the gravitational force downward. But the spring force upward is bigger than the gravitational force downward. And then when it's up here, the restoring force is the gravitational force downward minus the spring force upward, but the gravitational force is bigger than the spring force. So these two things, these two forces are combining to make a oscillating system, a system that can oscillate in simple harmonic motion. What I'm going to walk you through is the equation derivation for the energy, because there's a simplification of the energy equation that we can use when we're analyzing this situation with the mass hanging on the vertical spring. So we know our total energy is equal to 1/2 ky squared. So this is our, I guess I can write this here. This is our spring potential energy, and y is the amount of stretch from the spring's equilibrium position when there's no mass on it at all. Then we add our kinetic energy, which is 1/2 mv squared, and then we add our gravitational potential energy, which is mgy. So that's measured from, this is just established as the zero gravitational potential, or the zero reference line for gravitational potential energy. Remember that changes in gravitational potential energy are all we care about, so we don't really care where the zero line is. Now we know here that y is equal to z minus h. If you look over here, h is the distance that the block moves, or the spring stretches when the block is put on it. And so if we took the y position, or if we took the z position and we subtracted h, we would get y. So we're going to plug that into our y value right here and our y value right here. And we get this. E total equals 1/2 k z minus h squared plus 1/2 mv squared plus mg z minus h. Now we also know that at this position, the net force on the block is 0. There's the force of gravity going down, there's the spring force going up, and these two forces are the same. They're in equilibrium. So we have force of gravity down, spring force up. If I write my equation, my net force equation, I get negative mg. So the force of gravity is acting down, plus kh. This is Hooke's law. So k times the amount that the spring is stretched, which in this case we call h, is equal to 0. So when we isolate h here, we have h equals mg over k. We can plug that into here and into here, and we get this equation for total energy. Now I'm going to do some algebra here. We're going to square that out so that we get 3 different terms. And then from here to here, and you can pause it and look at it if you need to, we're just foiling, or is that what it's called? Distributing. This is called foiling. We're distributing the 1/2 k to each of these terms, and we're just distributing the mg to each of these terms. And so then we get this equation for the total energy of the system. 1/2 kz squared minus mgz plus 1/2 m squared g squared over k plus 1/2 mv squared plus mgz minus m squared g squared over k. So I want you to notice a couple of things. This right here is the same term. So there's positive 1/2 and negative 1. So we can combine them together and we can make that negative 1/2 m squared g squared over k. Also notice that there's a negative mgz and a positive mgz, and those cancel out. So that cancels, and then we're left with this. Now this whole piece right here, these are all constants. And since we only care about changes in total energy, we are going to just kind of ignore that because it's just a constant. So we get change in energy is equal to 1/2 kz squared plus 1/2 mv squared. So when you have a vertical spring, you can treat, this is basically all of the potential energy, and this is the kinetic energy. So you're basically combining your gravitational potential energy and your spring potential energy into one term, which is 1/2 kz squared. Now z is measured from the equilibrium position of the system, not the equilibrium position of the spring, and that's what helps combine those two together.